Dear students, welcome. Today we will delve into a core and fundamental topic in CFD, which is about the classification of governing equations and the method of characteristics. Before we start, let me ask you an intuitive question. Why does the wave equation, which describes the water waves, produce such different behavior from the heat conduction equation, which describes the temperature diffusion? One produces the sharp wavefront that can even turn into breakers on the shore, while the other spreads very smoothly. This difference is not accidental, it actually originates from the mathematical structure of the equations. That structure determines how information propagates in space, and it fundamentally determines how we should solve these equations on a computer. Now, first point, why is equation classification the bedrock of CFD? The answer to this particular question is that many beginners focus on grid generation, discretization schemes, algebraic solvers. That is natural. But I must emphasize that without a deep understanding of the mathematical type of your governing equations, attempts to build stable, accurate, physically realistic numerical solutions often end up being insufficient or might even fail. So, why is classification so crucial? There are four reasons to that. First, the equation type dictates the information propagation speed, finite, diffusive, or instantaneous across the whole domain, which directly determines the choice of numerical scheme. Second is that it tells us what initial and boundary conditions are well posed. Third, and the most important, is that it guides the selection of the appropriate numerical discretization, central differences for elliptic, upwinding for hyperbolic. And the fourth and the last one is that it directly links to the numerical stability. The CFL condition is derived from characteristic analysis. Now, at its core, CFD simulates how information travels in a fluid. We are not solving static equations, we are simulating how a physical quantity at one point influences another. In hyperbolic type of equations, information propagates at a finite speed along the characteristics. While in parabolic equations, the information diffuses. In elliptic equations, however, the information instantly affects the whole domain. A simple analogy is that think of a communication system in which hyperbolic is like a telephone call. Information travels along a definite line at finite speed, and a wavefront can stay sharp. While a parabolic is like heat diffusing in a metal rod, information spreads out and smooths initial perturbations. While elliptic is like a global meeting, any change at one point instantly influences the entire region. Everything is coupled simultaneously. Now, let me ask you a concrete question over here. Suppose you want to simulate a supersonic nozzle flow. What type do you think the governing equations belong to, and how should you choose your numerical method? So yes, the supersonic flow with the Euler equations is hyperbolic. Information travels downstream along characteristics at a finite speed. Therefore, you should use an upwind scheme that respects the direction of propagation. And the CFL condition requires that the time step be small enough that the numerical domain of dependence contains the physical domain of dependence. Now, let us go into more physical depth to understand the classification. We start from the journal second order linear partial differential equation in two independent variables as displayed. So here phi is the unknown. Subscripts denote the partial derivatives, and A, B, and C may depend upon the independent variables. So this classification depends on the sign of the discriminant. Here we would be representing the discriminant as delta, and it would be equal to b square minus 4 times a times c. So why the discriminant? In analytical geometry, the quadratic form ax square plus bxy plus cy square determines the type of the conic section. Partial differential equation classification borrows exactly this terminology, that is the elliptic, parabolic, hyperbolic, and the underlying mathematics is analogous. So the highest order derivative terms determine the character of the equation, just as a skeleton defines the basic shape of the body. So specifically, if b square minus 4ac is greater than 0, the equation is hyperbolic. Two distinct real characteristic directions would be there. But if b square minus 4ac equals to 0, it's parabolic, one repeated characteristic direction. And if b square minus 4ac is less than 0, it is elliptic, which means it would have the complex characteristics. Let us let us look at this particular classic examples, which involves the wave equation, the heat equation, and the Laplace equation. So, if we look at the wave equation, it is hyperbolic, while the heat equation, you would note that the highest time derivative is first order. The discriminant analysis is extended by treating it as a degenerate parabolic case, while the Laplace equation is inherently elliptic. So, what is characteristic in the xy plane through any point that are special curves? Uh, Along such a curve, the derivatives of the solution may become indeterminate, and the discontinuities in derivatives can occur when crossing it. Algebraically, the characteristic directions are those for which the coefficient matrix becomes singular. So, for a 1D wave equation, we can see this clearly, write it as a first order system, as we can see over here that the above equation partial u over partial of t plus c partial u by partial of x equals to 0, it is actually representing a right going wave, while the partial v over partial of t minus c partial v over partial of x equals to 0 is the left going wave. So the eigenvalues of the coefficient matrix are plus minus c, corresponding to two characteristic curves. Dx by dt must be equal to c, and dx by dt equals to minus c. So the curve dx by dt equals to c actually tells us that the information of the right going wave propagates to the right at speed c, while the other gives left going information. That is the physical meaning of the characteristics. They are the trajectories of information. Now, besides the discriminant, we can classify the systems using eigenvalues. For a first order system, partial u by partial of t plus a partial u by partial of x equals to 0, we examine the eigenvalues of the matrix A. If all the eigenvalues are real, the system is hyperbolic. If any eigenvalue is complex, it is elliptic or of the mixed type if real and complex appears together. So why does the reality of eigenvalues matter? The answer to this is that the real eigenvalues correspond to finite real propagation speeds, the basis of wave propagation. So complex eigenvalues imply no real propagation speed, usually indicating the instantaneous global influence of the elliptic problems. So the above analysis is primarily for second order linear PDE or the first order linear systems. For nonlinear fluid equations, we generalize to quasi-linear systems. A quasi-linear system is the one in which in where the highest derivative appears linearly, but lower order terms may be nonlinear. The Euler and Navier-Stokes equations are quasi-linear. For such systems, classifications is done by checking the eigenvalues of the coefficient matrix, and those eigenvalues generally depend on the solution itself, meaning that the same equations may be of different types in different regions of the flow. That is the classic mixed type problem in the transonic flow. Now, moving on to the elliptic equations and the physical world of the three equation types. So, now let us delve into the physical world of each type one by one. This is where we truly understand the CFD. Elliptic equations describe the steady state equilibrium problems. Their hallmark is that every point inside the domain is influenced by the entire boundary. Disturbance at one point instantly affects the whole region. Classic examples include the Laplace equation, which is the potential flow, maybe the representing the electrostatics, the steady temperature, while the Poisson's equation is the in CFD is essentially the pressure field for steady incompressible viscous flow that satisfies the elliptic equation, which is why solving the pressure Poisson's equation requires coupling across the whole domain. Now, elliptic problem characteristics are that it is the boundary value problem, which means that no initial condition is needed. Solution is smooth inside, which means that it would have no discontinuity. And numerically, implicit methods are necessary because information is globally coupled. Finite differences, finite volumes, finite elements all lead to large algebraic systems. Now, parabolic equations describe the unsteady diffusion dominated processes. The key is that the time direction is one way. The future depends only on the past, not on the future. So classic examples include the heat equation. In CFD, the most important application is the boundary layer equations. Proposed by Prandtl in 1904, the boundary layer splits the flow into a thin viscous region near the wall, which actually is parabolic, and an outer inviscid region. Because the boundary layer equations are parabolic, we can march from the leading edge downstream. Another application includes the parabolized Navier-Stokes equations. So by dropping the streamwise viscous derivatives, we actually convert the elliptic Navier-Stokes equation into a parabolic one, which can greatly improve the efficiency. So numerical traits include that it is marching in time. It is which means that it may be explicit or implicit schemes would be possible. So it is spatial information can enter via the boundaries, and most importantly the CFL condition, which determines the maximum time step for the explicit type of the methods. And the third type is the obviously the hyperbolic equations, which actually describe the wave phenomena. The most exciting and the challenging part of the CFD uh, is that the hyperbolic equations appear in the compressible inviscid flow. Generation and propagation of the shocks, sound waves, expansion waves, contact discontinuities, and the Riemann type of the problem. So the Riemann problem is very central in it is a solution of the conservation law system with discontinuities initial condition discontinuous initial condition. So it is the key to understanding the shock formation and the foundation of good enough type methods in the modern CFD. Along each characteristics, we define the Riemann invariants and combinations of physical quantities that remain constant along that characteristic. So using these invariants, we can predict the shock information and the propagation. So let me summarize all of this information we have just discussed. So as far as the property is concerned, all the of the information propagation, hyperbolic is of the finite speed, while the parabolic is diffusive. While on the other hand, the elliptic is instantaneously global. While when we talk about the initial and the boundary conditions, in hyperbolic case, we need both the initial and the boundary conditions. Likewise, the parabolic equations, while the elliptic only needs the boundary condition. As far as the characteristics are concerned, we in hyperbolic case we have two real characteristics. In parabolic case, we have one real repeated characteristic. while in elliptic we have none real characteristics. So moving on to the typical equations, hyperbolic type of equations would be represented by either the wave equation or the Euler equation, while the parabolic is represented by the heat and the boundary layer equations. And lastly, the elliptic equations are represented by the Laplace and the Poisson's equation. And the numerical tendency, we normally use the upwind schemes for the hyperbolic, central, or the implicit schemes for the parabolic type of the equations. And for the elliptic type of the equations, we normally use the implicit type or the implicit iterative numerical schemes. So these differences directly guide every choice when writing the CFD code. Now we enter a core part, the method of the characteristics. The central idea is that find special curves along which the PDE reduces to an ODE. So start with the simplest model, the 1D linear advection equation, which hereby is represented on this particular slide. So we look for the curves in x as a function of t in the xt plane, along which the total derivative du by dt equals to ut plus ux plus dx by dt. So compare it with the PDE. If we choose the dx by dt equals to a, and then du by dt would be reducing to equal to 0. So that is beautiful. Along the curve dx by dt equals to 0, u is constant. So that particular curve is a characteristic, and the PDE becomes the ordinary differential equation, du by dt equals to 0. So the initial profile simply translates at the speed without changing shape. So the solution is ux of t equals to ux x minus at comma 0. So now we move on to the standard steps of the method of characteristics. So the method of characteristics generally involve three steps. Number one is finding the characteristics. We solve for the dx by dt equals to lambda. Here lambda is representing the eigenvalue or the characteristic direction. The second step is establishing the compatibility relationships. Along the characteristic, convert the PDE into an ODE for how the solution varies. And thirdly, we integrate along the characteristics. We use the initial or the boundary conditions to obtain the solution. So for a linear system, this is often analytic. For non-linear systems, we usually discretize on a numerical grid. Now consider 1D wave equation as displayed, factor it as displayed, and we introduce the characteristic variable over here, which I would be pronouncing as zeta equals to x minus ct and eta equals to x plus ct. So in these coordinates, the wave equation becomes u as a function of zeta eta equals to 0. So with the general solution, u equals to function of zeta plus g function of eta equals to f x minus ct plus g x plus ct. Here f is the right going wave, g is the left going wave, while the characteristics x minus ct is equal to constant and x plus ct is also constant. F plus G are Riemann invariants, which means that the constant along their respective characteristics. Now let us derive the compatibility relations carefully, important for the compressible flow. Suppose we have a Cauchy linear first order system. A depends upon u over here. Find a left eigenvector u, eigenvector L of A, such that L times A equals to lambda times L, where lambda is an eigenvalue. Multiply this system and then defining a characteristic variable w such that dw equals to L times du. So along that characteristic dx by dt equals to lambda, we obtain dw divided by dt equals to 0. Thus, W over here is constant along the characteristic, that is the compatibility relation. For a Euler equation, the these particular relations actually reduce the complicated nonlinear systems to a few ODEs integrated along the characteristics. Now, going from the linear to nonlinear actually introduces the new phenomena. In a nonlinear hyperbolic system, the characteristic speed depends on the solution. For the nonlinear advection scheme, this particular equation, the characteristic equation is dx by dt equals to u, and u is constant along each characteristic. So the characteristic are the actually the straight lines, but different lines may have different slopes. This actually leads to the characteristic convergence, which means that the shock formation or discontinuity. Conversely, the characteristic divergence may lead to expansion waves or the rarefaction process. As far as the application to the supersonic flow is concerned, in steady 2D supersonic flow, the characteristics are the Mach lines. Lines making an angle u equals to arc sine of 1 over Mach number with the velocity vector. So these two families of Mach lines form a characteristic grid. The method of characteristics is actually used to solve the supersonic nozzle and the external flow problems. So we start from an initial data line and march downstream. So solving the compatibility equations along the two characteristic families. Important is that the method of characteristic only works for hyperbolic type of the partial differential equations. It is not applicable to elliptic or the parabolic type of the problems. And here we have a question that suppose we have the 1D Euler equation for the compressible flow. So how many eigenvalues does that particular system must have, and what is the physical meaning of each? So the answer to this particular question is that yes, three eigenvalues, lambda 1 equals to u, which actually would represent the material derivative or the contact discontinuity. The second eigenvalue is lambda 2 equals to u plus c, which is the right going sound wave, and the third eigenvalue is lambda 3, which is u minus c, so it would be representing the left going sound wave. So these correspond to the three information channels: advection by the flow, the sound waves propagating up, and the downstream relative to the fluid. Now, the moving on to the standard form of the 1D Euler equations, which is a part of the characteristic analysis of the Euler equations for the compressible flow. Now we tackle the most technical and the important part over here, which is the characteristic analysis of the Euler equations for the compressible inviscid flow. So these equations are a nonlinear hyperbolic system. Their behavior is far richer than the linear wave equations, especially when shocks and rarefaction appear. So the 1D Euler equations in the conservative form are represented over here, where rho is representing the density, u is the velocity, p is the pressure, E is representing the total energy per unit volume. So for the characteristic analysis, it is easier to write them in the quasi-linear form using the primitive variables u, which is equal to rho, u, and p, where A is representing a matrix in which we have the diagonal same as U, uh, and it can be seen that C over here is the speed of the sound, and gamma is the ratio of the specific speeds, and C is equal to under root gamma p over rho, whole under root. Now, eigenvalues and eigenvectors. So compute the eigenvalues as determinant of A minus lambda L equals to 0. So all eigenvalues are real over here. The Euler system is strictly hyperbolic, which means physically that U over here is the information that moves with the fluid particles. U plus C is the sound wave that propagates downstream relative to a fixed frame. U minus C is representing the sound waves propagates that propagate is propagating upstream. Now note that the role of the Mach number over here is equals to u over c. If the Mach number is greater than 1, which means supersonic, all eigenvalues must be positive. All information would travel downstream. But if Mach number is less than 1, which means subsonic, u minus c would be less than 0, and u plus c would be greater than 0. So, which means that one wave would travel upstream and the two would travel downstream. Now, moving on to the Riemann invariants, along each characteristic, we find the quantities that remain constant, which are the Riemann invariants. So, they are obtained from left eigenvectors. For lambda 1 equals to u, uh, dp minus c square d rho equals to 0, which means the entropy S is constant along the streamlines. While for the lambda 2 equals to u plus c, uh, derivative of it would be equal to 0, which means that the R2 equals to u plus 2c divided by gamma minus 1 equals to constant, while for lambda 3 equals to u minus c, the third Riemann invariant would be equal to u minus 2c over gamma minus 1 equals to constant. Now, as far as the application is concerned, Riemann problem, any initial discontinuity decomposes into three waves: the left going shock or the rarefaction, the contact discontinuity, uh, a right going shock or the rarefaction, while the second is the boundary conditions, in which the number of the incoming characteristic waves determines how many boundary conditions must be specified, and the third is a numerical scheme, which we normally are familiar with the Godunov type methods to solve exactly or approximately the Riemann problem at each cell interface. Now consider 1D nozzle with inlet Mach number of 2, which is representing a supersonic condition, and the exit Mach number equals 2.5, which is the subsonic condition. So supersonic region, all lambda would be greater than 0 down, which means that the downstream perturbations cannot influence the upstream. That is why a supersonic nozzle is governed solely by its geometry. Downstream pressure cannot propagate upstream. While a subsonic region, we have the one eigenvalue negative, which means that the upstream influence exists. That is why a subsonic nozzle design must consider downstream back pressure. Now, extensions to the 2D Euler equations, we have in the 2D steady flow, the equations are A partial W over partial of x plus B partial W over partial of y equals to 0. We examine the eigenvalues of the combination um, for any direction n x and n y. So if Mach number is greater than 1, so which means supersonic, all eigenvalues must be real, which means it is strictly hyperbolic. If Mach number is less than 1, which means it's subsonic, complex eigenvalues appear, and it mean that the elliptic or the elliptic and the hyperbolic mix type of the problem. And the if Mach number is equal to 1, which means sonic condition, we would have the repeated eigenvalues, the parabolic and the hyperbolic mixed type of the problem. So this explains why transonic flow is so challenging. The mathematical type changes from elliptic subsonic to hyperbolic supersonic across the sonic line. Now, moving on to the CFL condition and the numerical stability. Uh, Now we see how equation classification determines the numerical methods. First, the CFL condition, a must know for every CFD practitioner. The Courant-Friedrich-Levy condition, often abbreviated as CFL, in 1928 stated that the numerical domain of dependence must contain the physical domain of dependence. So in explicit time marching, this translates to delta t must be less than equal to c uh, times delta of x divided by lambda maximum, where lambda maximum whole determinant is the largest absolute eigenvalue, which is representing the characteristic speed. If the time step is too large, the numerical scheme misses physical information and becomes unstable. So as far as the hyperbolic equations are concerned, the CFL condition is very strict. For explicit schemes, CFL number is less than equal to 1 is typically needed for the stability in case of the hyperbolic equations. While for the parabolic type of the equations, we normally say that the stability condition is defined as delta t less than equal to uh, order of delta x whole square, which is much more restrictive and often also mean that the time step must be extremely small. While in case of elliptic type of equations, no time marching is in the pure sense. Implicit methods are most always used because the information is global. Now, moving on to the upwind schemes and respecting the information direction, for hyperbolic type of the equations, the upwind scheme is natural. In a partial u over partial of t plus a partial u over partial of x equals to 0. If a is greater than 0, the information travels to the right. The spatial derivative must be approximated using the left hand nodes. But if a is less than 0, it uses the right hand nodes. So why is upwinding so important? Using a central difference for hyperbolic type of problems lead to numerical oscillations or even blow up. Upwinding mimics the characteristic direction. Most modern high accuracy schemes such as VENQ, DG, and flux splitting methods are built on upwinding principles. So now we move on to the shock capturing and the artificial viscosity. For the nonlinear type of the hyperbolic systems, we must handle the shocks. Near discontinuities in the solution. So there are two main strategies to that. One is a shock capturing. We add the artificial viscosity to smear the shock over a few grid cells while retaining the high accuracy in the smooth regions. Von Neumann and Richmere introduced this in the 1950s, while the second main strategy is the Godunov type method, in which we solve the Riemann type of the problems at the cell interfaces exactly or approximately. So this approach directly uses the characteristic analysis. At each interface, we use an initial discontinuity problem to compute the flux. Now, what are the well-posed boundary conditions? Characteristic theory actually tells us that the number of the boundary conditions to be imposed must equal to the number of the incoming characteristic waves. So for the 1D Euler equations, we would be discussing them one by one. For the supersonic inlet, which means that the Mach number is greater than 1. Uh, for the subsonic inlet, Mach number is less than 1. For the supersonic outlet and as well as for the subsonic outlet. So for the supersonic inlet, we can see we have the three incoming waves. So which means that we would have the three total number of the boundary conditions needed, which, for example, the total pressure, total temperature, and the flow angle. While if we have the subsonic inlet, we would have the two incoming waves alongside with the two boundary conditions. Uh, and if we have the supersonic outlet, we would have the zero incoming waves, so we would have zero boundary conditions needed, and all would be extrapolated over here. So, lastly, the subsonic outlet, which means that the Mach number is less than 1, we would have one incoming wave. So the we would have one in sense of the back pressure as the boundary condition needed. So this is not arbitrary. It is actually dictated by the method of characteristics. Now, if you are simulating a rocket nozzle with the supersonic flow throughout, what numerical method and boundary condition would you choose? The answer to this is simply yes. The Godunov type upwind scheme. At the inlet, we must specify the three conditions: total pressure, total temperature, direction. While at the outlet, no boundary condition, extrapolate everything. We would ensure that the grid resolution is sufficient to capture any shocks that might appear. Now we move on to the Navier-Stokes equations part and the challenge of the mixed type. So we would be discussing the nature of the mixed type of the PDEs in this particular section. Finally, we come to the ultimate problem, which is the Navier-Stokes equation. So they are the mixed type. They contain the hyperbolic, parabolic, and the elliptic features simultaneously. If we see over here that the convective terms, partial rho u by partial of x, is actually representing the hyperbolic, which means that the finite speed propagation. The second is the viscous term. Mu partial square u over partial of x square is actually hyperbolic, which means diffusion term. The third is the pressure in the incompressible flow, which is representing the elliptic. Instantaneous global coupling. And the fourth is the time derivative partial u over partial of t, which makes the whole system parabolic in time. Now, the type is not fixed, it depends on the local Mach number. High Mach number means depicts that the convection dominates, which is mainly hyperbolic. Low Mach number depicts the diffusion, and the elliptic pressure dominates, which represents a parabolic elliptic type. Near the walls or the boundary layer, viscous effects, so we would say the parabolic, and in case of the far field, nearly inviscid, so it would be hyperbolic. Thus, the same Navier-Stokes equations can behave as different types in different regions, a huge challenge for the CFD. Now, moving on, the numerical strategy is that in modern CFD we tackle this with a divide and conquer approach. Convection scheme, the upwind schemes, Riemann solvers, flux splitting respect the characteristic directions, while for the diffusion viscous terms, we use the central differencing parabolic terms are straightforward. For the pressure velocity coupling, we project the projection methods, or the pressure Poisson's equation, which is elliptic, requires the global solve. And the fourth is the time integration, which is explicit for the convection. CFL is limited, implicit for the diffusion, and the pressure allows the larger steps. So this is often called as implicit explicit, so which is often abbreviated as IMEX. So this hybrid strategy respects the local mathematical nature of each term. Now, moving on to the section in which we would be discussing the recent advances and the concluding all of this discussion together. So, recent advances include the machine learning and the PDE solving through it. So, machine learning is changing the partial differential equation solving. Physics informed neural networks, PINNs, is one of them, which embed the PDE as a loss function, handle the mixed boundary conditions and complex geometries naturally. The second one is the operator learning, which we normally see as deep or net Fourier neutral operator. So, in which we learn the mapping from initial conditions to solutions, enabling the ultra fast predictions. The third is the data driven turbulence models, in which we learn closures from the high fidelity data for RANs or LES methods. So challenges remain generalization, stability, physical constraints, but machine learning is undeniably changing the CFD landscape. Now, equation classification can also affect the high performance computing and the massive parallelism. Hyperbolic or the explicit type of the equations, which are naturally parallel, each grid point updates using only the neighbors. Communication is regular and can overlap with the computations. The second are the elliptic type of the equations or the implicit types. Global solves require global communication. Advanced techniques like multigrid and domain decompositions are needed, while the third one are the mixed type of the Navier-Stokes equations, which in which we use the modern solvers use explicit convection plus implicit diffusion. Splitting achieves high throughput on the GPUs and heterogeneous architectures. Now, let me wrap up. PDE classification is not a mathematical abstraction, it's a logical foundation of the CFD algorithm design. The three types tells us how information propagates, how to set the boundaries, and which numerical scheme to choose. Characteristic analysis of the Euler equation reveals the wave mechanisms and gives the theoretical basis for the shock capturing schemes. And lastly, the mixed nature of the Navier-Stokes equations forces us to adopt the divide and conquer strategies. So whether you use the classical finite volume methods, high order DG method, or even machine learning based PDE solvers, classification theory remains the yardstick for judging whether a method is physically and mathematically sound. So this is all from this particular lecture. See you next time. Thank you.